Good morning. Hope everybody's doing well. So we finished up naming and nomenclature. Before we move on to chapter 9, I just want to ask if anybody has any questions off of nomenclature and naming, or if there's anything that they want to specifically go over from nomenclature and naming, like, oh my gosh, I'm so bad at naming acids or whatever. If not, we'll move forward. Okay. Well, if at any point we do have questions, feel free to ask. So the next chapter is, we're skipping chapter 6 and 7 and 8. We'll come back to those chapters. Don't worry. You don't want to do those chapters right now anyway. That's for the test 3. Those are a challenging set of chapters. But we're going to move to chapter 9, which is all on electrons. So we're going to sort of say goodbye to, well, I guess last chapter we said goodbye to math as well, but we're going to continue to say goodbye to math for this section. Don't worry though, math will come back in full force next time. So we've talked about, we've talked about atoms, we've talked about molecules, we've talked about changing neutrons, we sort of have talked about electrons a little bit, but we're going to spend some more time here just focusing on electrons, because even though they're tiny, they are super important, and the fact that they have a charge, that they're on the outside of the nucleus, all these things lead to chemical bonding, so very important stuff. So back in 1937, here's a picture of the Hindenburg. And this happened in New Jersey. There was quite a few people who passed away. In this case, they had a blimp that they filled with hydrogen gas, which is not a good idea, okay? Next time you have a kid's party, don't fill the balloons with hydrogen gas. It is very, very flammable. So the thing caught on fire. Instead, we like to fill our blimps, now modern day blimps, with helium, which is an inert gas. And if we look on the periodic chart, hydrogen and helium are like relatively close to each other, right? And we can sort of get into the mindset of, oh, well, they're right next to each other, so they must be very similar, but that is not the case. Hydrogen has a proton and 1 electron. Helium has 2 protons and 2 neutrons and 2 electrons. The fact that it's got those 2 electrons is heavily stable or highly stable, so much less reactive. Remember things that are in the same column. So hydrogen is much more similar to sodium, which is 2 down in activity than it would be to helium, which is its neighbor to the right or left. So what is about helium that makes it inert versus hydrogen being so reactive? Another thing, why does elemental hydrogen exist as a diatomic molecule? So we said hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, all those guys form diatomics, or they stick to themselves. Why is that the case? This all has to do with their electron configuration. So are there other elements out there that are as reactive as hydrogen? Oh yeah, all the things in column 1 are going to have a similar reactivity. Lithium, sodium. Are there other things that are inert, like helium? Yeah, all the noble gases. So neon, argon, krypton. As they get a little bit bigger, xenon, radon, those can be a little bit reactive. So before we get into electron configuration and the application of this to the periodic chart, we're going to do just a little bit of background talking on electron configuration, electrons and the magnetic spectrum. So this may feel like it sort of is deviating, but it will come back around. So when looking at electrons and atoms, there are two different models. The first model is called the Bohr model. Now the Bohr model is the more simplified version. If you've taken chemistry in high school or taken like a really watered down sort of chemistry class, you would see it as the Bohr model, which is like the solar system. So we've got the solar system model. So we've got the nucleus in the center and the electrons are like planets sort of spinning around. The second one is the quantum mechanical model, which is a more advanced model. It sounds more advanced, it is more advanced. And it talks more about the probability of where electrons exist because we don't actually know where their point in velocity is in space. Both of the models are useful. The Bohr model is useful, but it's not really what's happening. The quantum mechanical model is going to be a little bit more complicated, but it explains more. So we will end up doing more with the quantum mechanical model than the Bohr model. So the Bohr and Schrodinger and Einstein as well played a role in the development of the quantum mechanical model, but they were sort of bewildered by their own theory of this thing called wave particle duality of an electron. You'd want to take, a physics class to sort of get into the details of this, but the gist of the wave particle duality of an electron is that an electron will behave like a particle. Well, it behaves like a wave when you're not observing it. So if there's no camera or if a person isn't observing it, it will behave like a wave where it have sort of an infinite number of possibilities where the electron can be in space. But when we observe it, when we're looking at it, we actually have, for whatever reason, some sort of effect on the electron by observation, and the electron will, its wave of possibility will snap down to one point. So our observation actually has an effect on the electron, or some way of us viewing it has an effect on the electron. It's really, really crazy. This is a very crazy concept. And if you've not heard of it, I would definitely recommend looking up wave particle duality stuff and the double slit model or experiment, which goes into it in more effect, but it's sort of this idea that we as observers have an effect on the world around us. So we've got to talk about the electromagnetic spectrum. So the electromagnetic spectrum or electromagnetic radiation is the full spectrum that we can have energy existing in. So light is a type of energy and it has a specific speed, 3.0 times 10 to the 8th meters per second. Light will have properties of both waves and particles. Let's take a look at so here's sort of an analogy. When a water surface is disturbed, so if we have a droplet that disturbs the water surface, waves are created that radiate outward from the site. The waves carry energy as it moves through the water. So this is how we would transfer energy as a wave. So if you're a little bug sitting right here, the energy from this droplet falling gets transferred into a wave, and the wave will sort of bob the bug up and down. So when looking at different wavelengths or pieces of energy that have different wavelengths, your wavelength is your crest to your crest or your trough to your trough. Okay. It's symbolized with this little weird sort of italicized H, which we call a lambda. The wavelength is important because it tells us something about how much energy a wave has. The longer the wavelength, the lower the energy. The shorter the wavelength, the higher the energy. So as far as different types of visible light energy, red light has a much longer wavelength than, say, violet light or purple light, which has a short wavelength. So if we're looking at white light coming off of the sun or coming off of, let's say, like an incandescent light bulb, that will contain all the wavelengths of light, or the full spectrum. And we can see this happening when we run light through a prism. In nature, it happens during a storm when we have a rainbow. So the light from the sun will pass through water droplets and split open so that you can see the full light spectrum. So within that white light that's shining down on us from the sun, we do have red, orange, yellow, green, blue, indigo, and violet all in there. That's why we can see red, orange, yellow, green, blue, indigo, and violet around us in the world, because that light is allowing us to see it. If we use something like a black light only contains certain wavelengths. It doesn't have the full spectrum. That's why you can't see certain colors in black light. So red light has the longest wavelength of 750 nanometers. Nanometers is a tiny distance, but in comparison to violet light, which only has 400 nanometers, it's much longer. I don't expect you guys to have the wavelengths memorized, but you will need to know them in relative order to each other, okay? So you'll need to know red has a longer wavelength, gammas have shorter wavelengths, things like that. So I have a light source, I run it through a prism, and I get the full spectrum of color. This is sort of interesting. This goes back to that black light thing we were talking about, but a red shirt. So this woman sitting here at the beach has a red shirt on. The reason that the red shirt appears red is not because the shirt is like innately red. It's because the chemical composition of the shirt absorbs all the other colors from the natural light and reflects red light off of it. So the shirt, you could say the shirt is actually everything but red, right? It's sort of absorbed everything, and then it's shot the red back at you, and your eyes are picking up that red wavelength off of the shirt. So it's like the most unread shirt ever, which is kind of neat to think about. But that's also why if because of this chemical composition of this shirt, let's say it absorbs everything, it only likes to reflect red light. Well, if we put it in an environment where the light shining on it doesn't contain any red wavelengths, the shirt will no longer appear red because it can't reflect the red. So frequency is another thing that goes along with wavelength. The frequency of light, sometimes you see it as this V, or they call it nu, is defined as the number of cycles or crests that pass through a stationary point in 1 second. So wavelength and frequency, wavelength and frequency are inversely related to each other. So if you are sitting at the beach and or like we're in a wave pool or something, and the waves are really long, your experience is going to be that you bob up and then you come down and then you bob back up, right? It's this sort of slow, calm process. So your wavelength is really long, your frequency is really short, okay? So inverse. If you're in a wave pool and your wavelength is very, very short, so let's say we're in that same pool, but they've changed that wave pool setting and you're going bob, 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 and you're bobbing up over and over and over again, really, really fast. That means that your wavelength is short and your frequency is large. You have a lot of them happening over a given period of time. Frequency is directly related to energy, okay? So just like when we were in that situation, the wave pool with the really long waves, bob, bob, right? It's nice and calming. It's a low energy environment. When you're in that wave pool and it's short wavelength and you're going bob, 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 up, 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 that's a high energy environment, okay? So the way that those things relate to each other, long wavelength, low frequency, low energy. Short wavelength, high frequency, high energy. So with light, we can view it as a stream of these little particles or these little packets of light that we call a photon. So they're a particle in that they're an individual packet known as a photon, but they're acting as a wave because they have a different amount of energy that's carried through this wave process. So the amount of energy carried within each of those packets or those little photons is dependent on the wavelength of the light that you're dealing with. So if I have a photon that is containing, let's say, a shorter wavelength, it's going to have a higher energy. Maybe it'll be purple light. If I have a photon that's carrying a longer wavelength, it'll have a lower energy. Maybe it's red light. Okay, or maybe it's even outside of the visible spectrum. So let's look at the full electromagnetic spectrum. You guys do want to know or have access to the ordering of this, understand how it's ordered and how it works. So here's the visible light. They have it, that's not fine. Here's visible light. They have it expanded out, but in actuality, visible light only takes up a very narrow range in our full electromagnetic spectrum. So here's the lowest end of the electromagnetic spectrum. Here's the highest end. And then visible light sits right there. And conveniently, visible light is also harmless to biological material, or at least carbon-based biological material. And it's also what our eyes can see. So not a coincidence. We've got, let's say we're at the red end or the long wavelength, because purple is shorter wavelength. So we're at the longer wavelength. If we go just outside the visible spectrum, we move into this thing called infrared radiation. And infrared radiation is, our body gives it off in heat. We can't see infrared radiation, but there are pieces of equipment that we can use to see infrared radiation. And there are certain animals that see infrared radiation. This is a harmless form of energy. The wavelength is really long. So we're good with that. If we go a little bit longer, we move into microwaves. We use microwaves for a bunch of different things, but this is in fact the wave that they're talking about in your microwave. The cool thing about the length of a microwave is that it is the perfect length to run through a material and knock into all the water molecules. So the wavelength of this energy will penetrate into your food, and it doesn't decimate the food, but instead what it does is hit all the water molecules that are existing in that food. And if you hit the water molecules and the water molecules start to spin, what you do is you create thermal energy, or you heat the food up. So that's how you're heating your food up with a microwave. If you have something dry that you put in a microwave, it won't heat it up. If we move past microwave, we move into radio waves. Radio waves are really long waves and very low energy. Right? If we move, so we've got radio waves, microwaves, infrared, then we move into the visible light spectrum. So we go from red light all the way over to purple. If we end on the purple light here and we move past purple light, we move into ultraviolet radiation or UV radiation. So in this direction, the wavelengths are getting shorter, the frequency is increasing, and the energy is getting much higher. So within this visible light spectrum, we are sort of at a healthy level of energy. Everything longer than that is harmless. When we start moving into the higher energy wavelengths, this stuff starts to have an effect on our biological material. So ultraviolet radiation, it feels really good. If you have a little bit of it, it gives you a tan. Right? If you have too much ultraviolet radiation, it'll give you a sunburn. And if you have exposure to it over and over and over again, depending on your genetic makeup, it can lead to skin cancer. So these higher energy wavelengths can actually start to break down some of the genetic or our cellular material. If we move past ultraviolet radiation to an even shorter wavelength, we move into X-rays. And this is, in fact, the X-ray that they use to see your bones. This is such a high energy wavelength that it can permeate through your softer cells and then bing up against your bones. Now, when you get an X-ray, where does the technician go? They don't hang out in the room with you, right? They go behind a concrete wall or a lead barrier because you don't want to have regular exposure to X-rays. You get one every now and then, you're going to be fine, but you definitely don't want to be in the space of an X-ray over and over again daily. Even when you get an X-ray, usually they give you like a lead pad to put over your special areas because your reproductive spaces are highly susceptible to X-rays. If we move even higher energy than X-rays, we move into gamma rays. And that sounds really kind of cool and futuristic and stellar. Well, a gamma ray is actually the energy that is coming off of the sun. So very, very high energy particles. This is not something you want to be regularly exposed to. We can find gamma radiation happening off of nuclear situations like nuclear power plants and atomic bombs. But stars produce a lot of gamma radiation. We have a thing outside. If you look at the Earth, there's the atmosphere that holds all the oxygen and nitrogen and our gases. And then around that, farther outside of that, we have this thing called a magnetosphere, which sounds like it's out of like a Wolverine movie or something, but it's actually a real deal thing. And the magnetosphere, which is we have, because we have a liquid core that moves metal, it creates this current where we have this sphere of like a magnetic field. And that is really important. The magnetosphere is very, very important because it actually deflects most of the gamma radiation from the sun. So we're not experiencing gamma rays at a high level on Earth's surface. So they kind of go through all the stuff that we just talked about. Okay, so let's look at this and arrange these in the correct order. So arrange the three here types of electromagnetic radiation. We have visible light, X-rays, and microwaves in increasing order. So I want you to start with the lowest wavelength or shortest wavelength and then go to the biggest wavelength. Then I want you to do it for frequency and I want you to do it for energy. So put those in relative order. I'll give you a minute to do that. Okay, So the first one, so arrange these. Arrange the 3 types of electromagnetic radiation: visible light, X-rays, and microwaves in order of increasing wavelength. So we're going increasing. We first want to find the shortest wavelength. So of those 3, the shortest wavelength is going to be X-rays, then it'll be visible light, and then it'll be microwaves. Frequency will just be the inverse of that. So how frequently are we going to see these waves? Well, the lowest frequency is going to be the microwave, then it'll be visible light, and then it'll be X-rays. And then as far as energy per photon, that is directly related to frequency. So the lowest energy is the microwave, then visible light, and then the highest energy is the X-ray. So you will want to be able to sort of know ordering of that, or hey, which has more energy, yellow light or purple light? You'll be able to say purple light has more energy. All right. So this whole thing with electromagnetic radiation kind of feels a little random, like weren't we talking about electrons? Well, we're going to bring it back around to elements in chemistry. So each element on the periodic chart has its own atomic emission spectrum of light. Here we've got a neon light. Neon atoms inside a glass tube absorb electrical energy when you plug it in, and then they will reemit the energy as a red light. So there's neon has a consistent color of red. When you see a neon light like this, the red is actually the only thing that's neon. That blue is, I'm trying to think, it's mercury blue. I think mercury might give off a blue color, but they're different materials giving the different colors. So here, yeah, mercury on the left is giving off a blue light, and then hydrogen, when we excite it, is giving off of a pink light. If we look at the emission spectra of each element, they aren't continuous like natural light. They have incremental kind of pings or areas where they're giving off light. So here would be a spectrum. If I was to take white light or natural light and spread it open through a prism, I'd get all points on the spectrum. When we look at hydrogen light, what we find is that there's these empty pockets where that light doesn't exist, and we end up only having a little line here at like the orange, light blue, dark blue, and one at the purple range. As we move into helium, we've got a series of lines as well, couple more lines than we did with hydrogen. And then if we go into neon, we can see that we've got quite a few lines, but again, we don't have the full spectrum. Why these lines are showing up where they're showing up is based off of how many electrons each of these things has, and how the electrons are getting excited when we plug it in. So if you were to stand underneath a hydrogen light, for instance, and you had a green shirt on, you wouldn't be able to see your green shirt, or it would show up as a different color because there was no green light to reflect it back. It's just missing that wavelength. So if I take the hydrogen lamp over here and I run it through a slit and then run it through a prism, it will spread out and we will only have color at very specific points. And this is the case for any hydrogen. So if I had an unknown sample of a gas and I wanted to know what it was, I could run it through a prism and look at its spectrum and compare it to a spectrum that we have already in an appendix and determine what it is. So this idea of like, why is hydrogen, for instance, giving us a red light? Why is it giving us a blue and a purple? Led to this idea of the Bohr model. So here is the simpler Bohr solar system model. So we have our nucleus in the center, and then we have these things called orbits, which sounds very close to orbital, which is from the quantum. So just know that this is the orbit. In each orbit, there is a definitive space, and the electron is sort of floating around on that orbit. So N1, closest to the nucleus, is the lowest energy orbit. N5, in this case, is the highest energy orbit. Why does it get higher in energy as you move away from the nucleus? Well, what's the charge on an electron? An electron has a negative charge. The nucleus has an overall positive charge. So the electrons and the nucleus are attracted to each other. So this inner layer of the onion is much easier for the electron to hang out there. If I want the electron to say move into the N4, you have to put a certain amount of energy in it to get it to hop out because you're having to pull that attraction. In the Bohr model, energy is quantized. And what that means is that there's these quantum numbers of 1, 2, 3, 4, 5, and we can think of them as like rungs on a ladder. And you're either existing on the N1, the lowest energy, or you've hopped to the N2. You can't exist in between those energy layers. So you're either on orbit 1, orbit 2, orbit 3, so on and so on. We're not going to be at orbit 1.5. All right, so going back to this image, we're never going to hang out like right here. We're always going to be either at the 2, or actually the 3 or the 4. We won't be at like 3 1/4. So why are we getting those specific light emission spectrums? It's because when we plug in a lamp that has hydrogen in it, the electrical current will excite the atoms. And when we excite the atom, the electrons will move to a higher energy orbit. So let's say that we've got this electron here and it's sitting at the N1. And now it's going to excite out to the N3. When it gets excited, because it's like got all this energy, it moves up. When it relaxes back down, because let's say that current of energy has now moved to an adjacent atom or it's somewhere else, that electron will need to relax back down. It's going to go from the higher energy state back down to the lowest energy state. When it relaxes, it has to release that energy. And the way it releases the energy is in the form of light. Okay? So we've got this little electron, it absorbs energy, it pops up to a higher orbit. Then when it relaxes back down, it releases light. The type of light that it releases is based off of how much energy it has. So if you have an electron that is excited all the way to that outer orbit, it's got a lot of energy. When it relaxes back down, it's going to release a lot of energy. What has the higher energy light color? Purple. If it only hops to just like one orbit above it and lowers back down, it'll be a lower energy light release, which would be something like red. So when looking at hydrogen has only one electron, right? One proton, one electron, and that electron can excite to the N2, the N3, the N4. There's only a couple options for it. For example, if we look at the line that's at the 486 nanometer emission, that's where it's relaxed from the N4 down to the N2, okay? Versus if we look at the 657, that's where it relaxed from the N3 to the N2, okay? So looking at it in a visual way, we've got our electron, it excites, and then it comes back down here. This wasn't a very big jump, so it releases a lower energy light, or the red. Here, we've got a little bit of a higher excited electron possibility. When it relaxes down, it's going to give us a blue-green, and then we've got the really high energy violet. And that's why we get the lines just there, there, and there continuously anytime we have hydrogen. So, oh my gosh, this model that's talking about electrons, this Bohr model, is explaining this spectrum, why hydrogen has these lines at these specific points. This is amazing, right? So the great success of the Bohr model, everybody was so amazed by it. The problem is that it falls apart after hydrogen, so it doesn't really work to predict any other atoms on the periodic chart. So they had to come up with something that was more sophisticated. That's where the quantum mechanical model comes into play. But they still use the Bohr model to teach chemistry, usually in like high school. They'll teach you it that way, where you've got, you know, the solar system model, where you've got the electrons circling around. But we are going to spend most of our time in the quantum mechanical model. The difference between, I mean, there's a lot of differences, but one of the differences is that instead of having orbits, or these like little paths, we now have what's known as an orbital or a quantum mechanical orbital. Yeah, we added ALS, and that has a big difference. Orbitals, instead of orbits, orbitals are these areas of probability, okay, where we think the electron is going to hang out. We're like, I've got like a 95% idea that the electron is hanging out in this bubble right here. Or it shows us a statistical distribution of where we would expect the electron to likely be found. Why do we need something that's talking about probability? Don't we know where the electrons are around an atom? No, we actually don't. And that's one of the crazy things about some of these small particles is that we don't actually know a whole lot about them. So quantum mechanics revolutionized physics and chemistry. It revolutionized science in general up until this day even. Electrons do not behave like particles flying through space. So that whole planet solar system from the Bohr model is not true. We don't in general know their exact paths. So we may know where an electron is currently, but we don't know where it's going to be in the next millisecond. It's not going to move forward like a baseball being thrown. So an orbital is a probability map that shows us where the electron is hopefully likely to be found. It doesn't represent exact paths. So if we look at baseball, okay, on a macroscopic scale, like on a human-sized scale. So when this gentleman throws the ball, we can see the path of the ball and predict where that ball is going to go, unless he's like really, really good at throwing a curveball. It'll sort of follow this straight line. This is what the Bohr model was showing. It's easy to trace the path of the electron. That is not what's happening in the quantum mechanical world of the electron. The catcher doesn't actually know where the ball is going to end up after it's been thrown. He has an idea. He's like, I think it's going to be in this area, but he's not really sure. So he doesn't really have any way of putting his mitt in the exact right place. But if he keeps track of the catcher throwing hundreds and hundreds of these electrons over a certain period of time, he'll be able to create a statistical pattern where he's like, okay, I don't ever know exactly where it's going to be, but I have a probability of where it's going to be. So for instance, the catcher is going to say, okay, there's a 40% chance that the ball is going to end up right here. But there's a 20% chance that it could like end up somewhere out here. And then there's, a really small percentage that the electron could end up like outside of the stadium or on the other side of the universe. That is possible. So if this is sounding weird, it is super weird. It's a very weird concept. So let's try and make it a little bit more practical and tangible, because it gets weird when we get into the physics side of it. But when we use it application-wise for chemistry, we can get a little bit more concrete. So principal quantum numbers for orbitals. So in the quantum mechanical model, we have a number and a letter to describe the orbital. So let me write something on here. So when we were looking at the Bohr model, we just had a number, right? We would say that the n equals 1, that we were in orbit 1. In the quantum mechanical model, you're going to have a number and you're going to have a letter, okay? The lowest energy orbital out there is the 1s orbital. It's specified by the number 1. The 1 tells us how high the energy is. And then the letter S tells us the shape of that orbital. So the N we call the principal quantum number, and it specifies the principal shell of the orbital. So are we in the lower energy 1 shell, the higher energy 2 shell, 3, 4, so on, so on. So a single electron that is hanging out in an undisturbed hydrogen. And when we say undisturbed hydrogen, we mean a hydrogen that hasn't been excited. We haven't plugged it in or lit it on fire or anything like that at room temperature. So we've got a single electron because we have a single proton that's going to live in the 1s orbital. We call this the ground state or the lowest energy state of the hydrogen atom. If we were to excite that electron in the 1s, we would say that it exists in a higher energy orbital or its excited state. Every atom out there has one ground state, one place where all the electrons are packed in the lowest energy orbitals, but it can have many excited states. How much energy did it get? The electrons can ping one step up, they can ping 3 steps up. So one ground state, multiple excited states. Energy increases with principal quantum numbers. So N1 will be the lowest energy, N2, N3, N4, we increase in energy as we move up. And then since the 1s orbital has the lowest possible principal quantum number, we can't have a lower number than 1. We would say it has the lowest energy shell possible. Why it's important to know the energies? Because we always fill electrons in lower energy shells before we fill higher energy shells. So this is closer to the center of the atom or where the nucleus is. It's easier to pack electrons in there than it is to pack in the 4. So we're always going to fill 1, then to 2, then to 3, then to 4. As far as the letter is concerned, that tells us the shape, and it also tells us how many electrons we can hold within each of those shells. So the possible letters are going to be S, P, D, and F. You do need to know the shape of S and the shape of P. You don't need to know D and F. Okay. While you're putting notes down, S can hold a maximum, that shape holds a maximum of 2 electrons. Okay. Can't put more than 2 electrons in an S. P can hold a maximum of 6 electrons. D can hold a total of 10 electrons. And then F, which we're not going to do a whole lot of work with F in this class, but F can hold a maximum of 14 electrons. So S is 2, P is 6, D is 10, F is 14. So as far as the shape is concerned, orbitals with the S subshell have a spherical shape. So let's look at the S orbital. Okay, it looks something like this. So our nucleus is in the center, and then there's this sphere shape that, again, represents like, 90, 98% of where we would expect the electron to fall. So the probability map shows as a sphere. If we look at it as a dot density over here on the left, you can see that the dots are thicker. There's more probability of it being closer to the nucleus. Then they sort of thin out, or they spread out. The probability spreads out as we move away from the nucleus. Not as likely that the electron is going to be this far out because it just takes more energy. So it's easier for it to sit there. So the number of subshells in a given principal shell is equal to the value of n. So if I am dealing with n equals 1, I can have a total of 1 subshell, or the S subshell. If I'm n equals 2, I can have a total of 2 subshells, which means I can have the S and the P, so 2 different letters. If I'm n equals 3, I have 3 options, S, P, and D. We'll always fill the S before the P and the D. N equals 4, I have 4 options, S, P, D, and F. So if I'm looking at the 1s orbital versus the 2s orbital, the difference here, they're both spheres, they're both S shapes. The 1s is a lower energy though, the 2s is a larger energy, which means it's also a larger shape. So you can kind of think of these as like Russian dolls being nestled into each other, or layers of an onion. So we would fill the 1s orbital first with 2 electrons. And then we would have this 2s orbital that would wrap around the 1s orbital. And then we would be able to put 2 electrons in there as well. This is how the p orbital looks, okay? The p orbital, I told you guys, can hold a maximum of 6 electrons. We call the p orbitals the dumbbell shapes. So the probability cloud looks like these little dumbbells, or like little balloon animals that have been twisted. And the Electrons, usually there'll be two. So there'll be one electron here and maybe one electron here, one here, maybe one here, and then one in this lobe and one in this lobe over here. So 1, 2, 3, 4, 5, 6. The dumbbell is a dumbbell in the X, in the Y direction, and in the Z direction. So it makes like a three-dimensional shape. This is not something that we like made up. This is just how it forms in nature. Okay, when we observe the electrons, this is how they like to form. Probably because the electrons have a negative charge, so they want to get as far away from other electrons as possible, and this is the most efficient way to do it. The next subshell, n equals 3, can give you the d orbital. The d orbital can hold 10 electrons. You don't need to know the shapes of it, though. You do need to know that it holds 10 electrons. Let's take a look at the shape of the d. This is what the d looks like. Okay, so we've got a four-lobed sort of four-leaf clover in the z direction, one of them in the x direction, one of them in the y direction, one at an angle, and then so we've got it. Then the last one is this like dumbbell with like a little donut around it. Okay, so this again, this is the probability. This is what it shows up like in nature. The electrons will probably be in one of these lobes. This gets a little complicated. That's why we don't expect you to have that shape memorized. And the F gets even more complicated. So we like the quantum mechanical model better because it will predict the light spectrum for all of the atoms as opposed to just hydrogen. Bohr did just hydrogen. So the quantum mechanical or wave mechanical model, this 1s2, 2s2 thing is has much more predictability power. There are some theories that go beyond the quantum mechanical model. So if you've done a lot of physics in the last 10 to 15 years, there are things that are sort of smushing the quantum mechanical model down, replacing it, but we're not going to go any farther than this. So if I'm going to write the electron configuration, this is where it kind of gets important in chemistry. I'm going to write the electron configuration. I always fill the lowest energy thing first, and then I start to fill the higher energies. So we know the lowest energy orbital is the 1s. So if we're looking at hydrogen, I have one proton, so I have one electron. So I'm going to fill the 1s, and I'm going to put a little number in the upper right-hand corner that tells me how many electrons are in that s orbital. And then, since it's hydrogen, we only have one electron. So I'm going to say I'm in the 1s orbital and I have one electron. So we would say 1s1. This is the electron configuration for ground state hydrogen. Sometimes they are represented in these things called orbital diagrams. It's just a more visual way of doing it. In an orbital diagram, you'll make a box. You'll put the orbital underneath it. So this is the 1s, and then you're going to add an arrow or a half arrow to represent an electron. Each box can only hold 2 electrons, and the arrows need to be in opposite directions. So because of this thing called electron spin, all the electrons are spinning equal and opposite of their partner. They aren't all spinning in the same direction. That would not work. So in an orbital diagram, the direction of the arrow pointing up or down represents the electron spin. And because of Pauli's exclusion principle, any orbital that has 2 electrons needs to have opposing spins. So you'll always draw the arrows moving in opposite directions. And I'll show you some more examples as we get into bigger atoms. So as far as filling, this is the way we fill: the 1s2, the 2s2, the 2p's, then the 3s, then the 3p's, then the 4s, then the 3d's, then the 5s, then the the 3d's, then the 4p's, then the 5s, then the 4d's. There's a certain ordering that goes in place, and it's not just as simple as you fill the 1 and the 2 and the 3 and the 4 and the 5. I'll show you how to get this thing memorized off of just looking at the periodic chart. You don't have to actually carry that information around with you in your head. So helium, here's helium. Helium has 2 electrons. So if I'm going to write its electron configuration, I'm going to write it as 1s with 2 electrons. If I was to draw the orbital diagram, I'd draw a box where with the 1s, we do 1 up and 1 down. Let's move to lithium. So lithium has 3 electrons. Okay, you can look at your periodic chart. It's got a proton number of 3, so electrons are 3. So in this one, I always fill the lowest energy shell first. You can kind of think of it as like you're piggybacking off of the atom before you. So lithium is 1 past helium, so it's going to be whatever helium's configuration is plus 1. So we fill the 1s and we put 2 electrons in there. Then I have to move into the 2s. Why can't I put 3 electrons in this shell here? Because how many does s hold? Only holds 2. Okay. So I've got the 1s2, and then the 2s, or the larger s orbital, will have 1 electron in it. Drawing out the orbital diagram, we'll make a box, arrow up, arrow down, and then the 2s only has 1 electron in it, so we arrow up. Let's look at some bigger ones. So carbon, for instance, carbon is number 6, so we have 6 electrons. So I need to fill 6 electrons into my configuration. The way that I'm going to do it, 1s2, 2s2, that's 4 electrons there. I have 2 more electrons. I'm going to put them in the 2p shell. Now, when drawing it out, the 1s gets 2 electrons, the 2s gets 2 electrons, and the p gets a set of boxes. It'll have 3 boxes because p holds a total of 6 electrons, so we need 3 boxes, 2 for each. Because of this thing called Hund's rule, when we're filling equal energy orbitals, so these 3 orbitals are in the same energy, we want to fill them in singularly first, and then we go back and double them up. So don't double this one up first and then single the rest out. Make sure you single them each. All have parallel spins, so arrow up, arrow up, arrow up, and then you get to fill in the arrow downs. So here is the ordering of how you fill. And I really hate this diagram, honestly, because I think it's super confusing and you have to like write it out. So I'm going to show you how to do it on the periodic chart. But this is how you fill it. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p, 5s, 4d, 5p, 6s, okay? They write it like this, and then they put these lines with like the arrows swiveling. But if you swivel your arrow in the wrong direction, your filling is going to be wrong. So let's just look at a periodic chart and figure out how to read this. I think they have one in the slides, actually. Let's skip forward. Okay. Great, yeah. So when you have your periodic chart, I want you to divide it into sections. Over here in the blue, and helium's sitting here, but I want you to put helium over here. Helium and hydrogen can kind of flip back and forth. So this over here is known as the S block. Okay? So this column here and this column here, we include in the S block. How many electrons can S hold? 2. How many columns are there? 2. Great. Okay. This pink area over here, minus helium, this is known as the P block. Okay, how many electrons can P hold? 6. 6, three sections, but each one holds 2 for a total of 6. How many columns do we have? 6. Okay. This thing in the center here, our transition metals, this is known as the D block. How many can D hold? 10. How many columns? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. And then all the way down at the bottom here, I've got the F block. F can hold 14, and there are, in fact, 14 columns. So when I want to fill, let's say we're going to go to aluminum. Okay, they've got some of the electron configuration there for you. Erase this here. Okay, let's say we want to do the electron configuration of aluminum. So in order to get to aluminum, I always start at the very beginning. I start at hydrogen and I read this like a book, moving through each section, filling as I go. So if we're going to go to aluminum, we start over here at the very beginning, hydrogen. We know that this is the S block. Do you guys see the period numbers? 1, 2, 3, 4, 5, 6, so on. That's the number that you're in. So the first thing we fill is the 1, and what block do we hit first? The S. So I'm going to fill the 1s first, and how many electrons do I have to fill? 1 and 2, so I'm going to put a little 2 there. All right, so we've gone through here, we've gone through here. Have we gotten to aluminum yet? Not even close, so we need to keep moving. So what's the next thing that we fill? The 2, and what do we bump into? The S, right? So we're going to fill the 2s, and how many electrons go in there? 1 and 2. So then what do we want to fill next? I'm still in the 2. I'm going to go across here to what is this block now? P block. So we're going to fill the 2p. Do I completely fill it? Oh yeah, because we haven't gotten to aluminum yet. So I'm going to put 6 electrons in there. 1, 2, 3, 4, 5, 6. When we get to the end of the line, just like you would in a book, go back to the beginning. What are we at now? The 3. My pen will work for me. The 3, and what do we bump into? S. So we fill the 3s. Then, and do we fill both of them? Yes, we do. So I'm going to put a 2 there. After the 3s, what do we bump into? The 3p. Now, how many do we put in this p? Well, aluminum only has 1 there. So the electron configuration for aluminum is 1s2, 2s2, 2p6, 3s2, 3p1. And you can just read it off the periodic chart. All right. Or you can memorize the ordering. I just find it more useful to be able to do this. Let's do something that requires some D's. So we'll do strontium here. So if I need to get down to strontium, I have to start at the beginning. And it's going to be the same configuration. You're always going to start it the same way. So we start with 1s. We have to fill both of those. Okay, so we go through the 1s. What comes after the 1s? The 2s. We fill it completely. What comes after the 2s? The 2p. And we fill all 6 of those. What comes after that? The 3s. And we fill that completely. After 3s, we go over to where aluminum was. That was the 3p, correct? 3p. And do we fill it completely? Yes. 1, 2, 3, 4, 5, 6. So we put 6 in there. Now pay attention here. So what happens after we go to 3p? We go to 4s, right? There's the potassium and the calcium. So we're at the 4s. 4s. We fill it completely. Now, what's the next thing? What block do we bump into? In this case, we bump into D, right? So we were at calcium, which was at the 4s. Now we're at scantium, which is the D. I want you to make a note here. D is always equal to n minus 1. So if we're in the 4th period, the D will actually be 3. It'll be the 3D. So this is 4p, this is 3d, this is this is 4s, this is 3d, this is 4p, okay? So we're not filling the 4d here, we're actually filling the 3d here. 3d, 10. We fill all of them because we're not close to strontium yet. Now, so think of your D as like one less than its snuggly neighbors. So these guys will always be one higher energy number than the D. So we had the 4s, we jumped down to the 3D, we completely filled that, and now we jump back to 4. and this is the 4p. 4p, do we fill it completely? We do. So we put 6 in there. Then we go over to here, we're at the 5s. 5s, and because we're at strontium, we will fill both of those, or we'll put a 2. So I think the trickiest thing for people is this right here. They sort of just instinctually want to put this as a 4D because it's 4s, well, then it would be 4D and 4p. The D is always going to be one less than its surrounding buddies as far as its number is concerned. So when I'm filling this in, I fill the 1s first, the 2s, then I bump into the 2p, then the 3s, then the 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4d, or 6s, 5d. Then we do the lanthanides, but I'm not going to test you guys on lanthanides. Okay, so the farthest we're going to go for class is barium. So if you can do the electron configuration for barium, you can do the electron configuration for all of them. So why don't we just do that? I want you guys to give me the full electron configuration for barium. This gives you just the last part. I don't want just the last part. I want the whole thing. I'm going to clear out of this. Make sure you've got your periodic chart. Or I'll leave this up. I want you to go to barium, and then I'm going to write it on the other slide when we're done. I'll give you 2 minutes. Okay, so we said we were going to do barium. Again, if you can do barium correctly, you can get the rest of them. So barium's sitting down at number 56. So I start at the very beginning where hydrogen is, and I know I need to fill in the 1s, and I'll fill it completely. Then going across, I get to the lithium section, that's the 2s, and I fill that completely. After that, I bump into where boron is, which is the p. So 2p with a 6. Then the 3s completely. Then wherever aluminum is, the 3p, and I fill that. Then the 4s. Then I fill the D, but it's a 3D. D is one less. We completely fill that. Then we go back to the 4p. Then where are we? We're over at rubidium. So we're going to fill the 5s. Then the 4D completely. Then the 5p. slide S over there, 5p. And then the 6s2. Any questions on that mess? On where the electron configuration came from, on how to get it off the periodic chart? If you can't figure out how to do it off the periodic chart the way I was explaining it with the different blocks and stuff, then just memorize the order. And if you know the order of barium, you can literally find anyone that's shorter than that, right? It's just some amount shorter. To go. We're going back to the slides. We skipped over some stuff here. Yeah, there's this thing, which I don't really ever use that. Okay, so a couple rules for writing electron configurations. We always fill lower energy orbitals before we fill higher energy orbitals. Orbitals can hold no more than 2 electrons each. When 2 electrons occupy the same orbital, they must have opposing spins. When orbitals of identical energy are available, all of these are first occupied singularly, and then we double them up. So let's look at some of the orbital diagrams for some of the bigger things. So nitrogen, which has 7, 1s2, 2s2, 2p3. So we would fill the 1s, opposing spins. We'd fill the 2s, opposing spins. We have 3 in the p here, so I'm going to fill it in singularly first. I don't want to put 2 here and 1 here. It makes it sort of lopsided. This gives them, in this capacity, the electrons can spread out farther away from each other, which they want to do because they're all negatively charged. Here we've got oxygen, 1s2, 2s2, 2p4. The only difference between these is that this has an additional electron. So we fill in a doubled there. Fluorine has 5. We fill in another one here. And then neon, when you look at its electron configuration, what do you see about its outermost shell? It's completely filled. That is very, very stable. So that is why neon doesn't really react with things, because it doesn't have any openings in its outer shell to like pair up with something. This thing here, it's got an opening here. This has like 3 openings. So these electrons can transfer and change because all of these things that don't have complete outer shells want to become like a noble gas. They want to get to a complete outer shell. This is very, very stable. So you may be wondering, okay, those electron configurations are so freaking long. Is there a way to abbreviate them? There is, but you need to be able to do it both ways, all right? So make sure you can do the full. But let's look at sodium. If we have sodium, sodium is 1s2, 2s2, 2p6, 3s1. You can abbreviate using the noble gas that comes before it, all right? So if we look at sodium, which is number 11, the noble gas that comes before it is neon. So I can take everything that is in the configuration of neon, which is this thing here, and I can substitute it by writing neon in brackets, all right? But I have to write whatever's left over after it. I can't just write neon, because if I write neon, then I'm saying that sodium has neon's configuration. And in this case, it isn't charged, so it doesn't. So we take whatever the noble gas is before and then add the junk that follows it. So that real long one that you wrote, barium, I want you to write it as an abbreviated version. So you've got your barium. Should only take you a minute here. Okay, so here's barium, super long, total pain in the butt. to write that whole thing out. So what I can do is I can see that, that actually all of this is the same configuration as the noble gas that came before it, which is xenon. So I could say that barium has the electron configuration of xenon with whatever's left over, 6s2. Don't forget that. You probably like doing it better that way. It's a little faster, but make sure you can do it both ways. Any questions on configurations or abbreviations? Make sure that you feel comfortable or will be comfortable with doing electron configurations for anything all the way through barium. And that will include orbital diagrams as well. And we'll do some orbital diagrams next time. If you have any questions specifically on this, speak up. Otherwise, we'll cut it there for today and we'll finish some of this stuff up on Wednesday. All right, if you have a question, stay around. I will be here. Otherwise, enjoy the rest of your day. Okay.